Okay, the next problem is given in the sheet that I distributed in class for polar coordinates. Now this is sample problem 2/10. In this problem you actually have a radar. So this is your radar that is tracking a rocket. Okay, so this rocket is somewhere here. It's unpowered, right? It's unpowered, and you look at the this is your R. This is theta. Right? The rockets go in this direction, so you do have positive R direction, positive theta direction. Okay, so the tracking radar lies in the vertical plane of the path of a rocket, which is coasting in unpowered flight. So there's no thrust provided by the rocket above the atmosphere for the instant when theta is equals to 30 degrees. R, which is the distance from the radar to the rocket, is 250,000 feet. R dot is 4,000 feet per second, and theta dot is 0.8 degree per second. Right? Remember, R dot is the change in R in the R direction, right? Change of R in the R direction. In other words, there's a change in R. Acceleration of the rocket is only due to gravitational acceleration, and for this altitude of this rocket, the gravitational acceleration is 31.4 feet per second squared. Calculate velocity of rocket at this instant, and R double dot and theta double dot. Okay. All right, the first part, part A. For a polar coordinate, the way to calculate velocity is the same as for any other coordinate system, except we're going to use different component. Instead of n and t, we're going to have r here and theta here. So Vr is the velocity of this rocket in the r direction, and V theta is the velocity of the rocket in the theta direction. Now in this case, remember, the theta is positive in the clockwise sense, right? In a lot of instances, it is positive in the anti-clockwise sense. So in this case, it is clockwise positive. So for polar coordinates, remember, Vr is essentially just r dot, right? Vr is the velocity in the r direction, right? So r dot. So we already know what this is. This is 4,000. Right? So it's 4,000 feet per second. Okay. And V theta, as we remember from our cheat sheet, V theta is r theta dot. Okay. So I have an R of 250,000, 25 times 10 to the 4 times theta dot is given to me in degree per second. I do need to change it to radian per second. So this is 0.8, right, divided by 8,180 pi radian per second. Okay. So what I have here is 3490 feet per second. So you combine these two, what you get here is 5,310 feet per second. Okay, so this is my first part, the answer for the first part. All right, now for part B, you are asked to calculate R double dot and theta double dot. Now, I'm sure that a lot of you at this stage you're confused, like how do I find this? Well, if you think back, or if you look at your cheat sheet, you remember that these two terms appear in the acceleration in polar coordinates. So, for example, they appear in AR, which is the radial acceleration, and also in A theta, which is the transverse acceleration. So we're actually going to look at those in order to calculate R double dot and theta double dot. Okay, we'll leave this here. We have a record of it. All right. So for part B, A, right, is AR, is equals to r double dot minus r theta dot squared. Okay, so this is 1. And a theta is equals to 2r dot theta dot plus r theta double dot. Right? So from AR I can calculate r double dot, and from a theta I can calculate theta double dot. Alright? So AR. So A in the R direction. So I'm going to do something to this this graph now, right? A. So the only acceleration is this G. This is the only acceleration there is for this rocket because it's unpowered. So there's no thrust provided by the rocket propellant. Let me just do a bit of trigonometry. This is 30 degrees, right? So this is AR. So remember, this is your AR. This is your A theta, right? And of course, this is 90 degrees. This is 90 degrees here. So this is 60 degrees. Okay. All right. So this is 30 degrees. Okay. So AR. So what is AR in terms of G? AR is minus G cosine 30, right? So minus G cosine 30 degrees. So this is my minus G, right? Minus G pointing up because G is pointing down positive. Pointing up is minus G. If you resolve this to in the R direction, you get AR. Right? So AR is minus G cosine 30, so it's minus 31.4 cosine 30 degrees, and what you get here is minus 27.2 feet per second squared. Okay? Minus 27.2. And that's equals to r double dot minus r theta dot squared. Right? So I can actually calculate r double dot, since I already know r and theta dot. Right? Minus 27.2 plus r was 250,000 times theta dot squared, so this is theta dot, right? So 0.8 divided by 180 squared. Okay. So r double dot equals to 21.8 feet per second. That's r double dot. Okay, so the next part is theta double dot. So theta double dot comes from this equation. So let's figure out what is A theta based on trigonometry. So A theta is in this direction. Okay, so this is going to be positive number because A theta is nothing more than G cosine 60 degrees, right? G resolve in this direction, you get A theta. Okay. So it's 31.4 cosine 60 degrees. Right? This is half, so this is about what? Maybe 15.7, roughly like that. 15.7. Okay, so this is 15.7 feet per second square. And this is also equals to 2r dot theta dot plus r double dot. So 2r dot theta dot plus r theta double dot is equals to 15.7. Okay? So I know r dot, I know theta dot, right? These are all given to me. I know r, the only thing I don't know is theta dot, theta double dot. Right? So this is equals to 15.7 minus 2r dot theta dot divided by r. Right? And the answer is minus 3.85 times 10 to the minus 4 radian per second squared. So this is my theta double dot. Okay? So what you'll see here is that this is usually a very small number. Right? This is what we call angular acceleration, the change in the angle. Right? It shouldn't be very large because you're looking at something that's really far away. And hopefully it's not going too fast. I mean, usually it doesn't go too fast. It's just like you observing a plane flying in there, right? It seems to move really slowly, right? It's that thing about theta double dot.